In today's class, we'll be talking about two selected position sensors. We will start with a sensor that's called LVDT. LVDT stands for Linear Variable Differential Transformer. This sensor is very robust and very accurate. You can use it on production machines, you can use it in airplanes, you can use it in drilling platforms, and so on. It is composed of two parts. One part here, one component, is the fixed part that is attached to a frame of your machine, and this movable part is attached to the object or to the movable part. And the LVDT measures the absolute position. Let's take a look on our lab setup. Now the sensor that we will be using is this one. The length is a few hundred millimeters, and this is the slider. So this slider is moving left and right. And in our experiment we will move this ruler so that we can set a desired position, and we will read the output signal from our sensor. Now this sensor has a current output. It is one of the standard current outputs that we have been talking about. It has an output of 4 to 20 milliamperes. So we will measure the output current on an ammeter. Let's take a look on our setup and let's see how we will actually perform the experiment. Now you can see me moving the input to the position sensor. I'm moving the ruler, and during the experiment we will set different positions and we will read the current output as our signal. We will use an ampere meter to get the signal, and you will get the data that correspond to the different position. The second experiment that we will do is that we will fix the position of our slider, so we will have a constant input, and we will change the load resistance that we have in our current loop, and we will see for which resistance the current actually starts to drop. So in this way we can verify what is the maximum allowed resistance in the loop, so that we don't limit our range of the sensor. Let's take a look on the data sheet of this sensor. Now this is our output, 4 to 20 milliamps. Electrically it's done in such a way that there is one primary winding powered by AC current, and we have two secondary windings. The output signal is voltage that is proportional to the position, and in this particular LVDT that we will be using on our class, now there is an external electronic circuit that produces the standard output 4 to 20 milliamps. Now mechanically there is a spring that we have in the sensor, so it's pushing the slider against our object, and here at the end there is a rolling ball, so that the contact between the object and the sensor happens only at one point. You can see that this sensor has a very good repeatability, up to 2.5 micrometers. In general, with LVDTs, you can obtain a resolution of a few micrometers, and it can measure in ranges of starting from few millimeters up to few hundred millimeters. The second sensor that we will see today is a resistive position sensor. The one that you see in the picture is supposed to measure angular position. Here we can see the resistor with 2.7 kilo ohms, and this terminal is where we connect the power supply voltage. Those are the fixed terminals of our sensor. And this terminal in the middle is the slider, and this is where we will take the output voltage. Now on this picture on the right you can actually see the sensor itself from the bottom side. So this is the fixed terminal here and here, and it is connected to a resistive track. You can see here that this is my resistive track made from a resistive wire, and this is the slider, and the slider is turning like this. So if we change the position of the slider, we change the resistance that is between one of the two fixed terminals and between the slider that is here in the middle. So the output is a function that describes how is the resistance changing if we change the position. Now in our setup, we will use a linear position sensor. So this is the sensor itself. In a minute, we'll take a look in the datasheet what we can expect. And this is the slider that connects to your object. We will have a ruler, and we will move the ruler, and we will set some predefined positions, and we will read the output signal. Now let's take a look on a video how this is actually done. Now you can see me moving the ruler, and at the same time I am holding the slider so that we have a signal on the output from our position sensor. We will set some known positions on the ruler, and we will get the output signal. In this experiment, we will use two voltmeters. One voltmeter will be a digital voltmeter, and the other one will be an analog voltmeter which has a much smaller input resistance. Let's take a look on a schematic of the connection. Here we have a 5 volt power supply. The whole experiment is powered by 5 volts, and this is my sensor. Now the one that we will be using has a resistance of 5 kilo ohms, and on the output we will measure the voltage on the slider and here between one terminal of the power supply. We will use two voltmeters. One voltmeter will be a digital voltmeter. This voltmeter has a large, very large input resistance, few mega ohms, and therefore compared to the value of the resistor, which is 5 kilo ohms, will be almost as if this circuit is unloaded. We will use this as a value of K, and I will have explained on the lecture what this actually means. And if we perform this experiment, we will get this straight line as our steady state characteristic. Now the input will be position, and the output is voltage. In this picture, it's normalized to position from 0 to 1, and for voltage from 0 to 1, where here for the voltage it is relative to the input power supply voltage, relative to 5 volts. So we can see that if the input resistance of my voltmeter is large, I have a nice linear steady state characteristic. Now the second data set that you will obtain will be measured with a voltmeter which has a much smaller input resistance. It is about the same value as the resistance of my sensors here, so 5 kilo ohms. And in this case you can see that here this is this magenta curve, and we have a very large deviation from linearity. So for this kind of sensor it is very important to use a voltmeter which is a very high input resistance. We can also plot the dependence of the relative error on the position, which is here this red curve, and we can find out that the maximum relative error is always in the middle of the range. And we can do the same analysis also for the absolute error, and we will find out that it's in about 2/3 of the range. Now for relative error, it does not depend on the value of K, it's always in 0.5. For the absolute error, it depends slightly on the value of K, but it's about 2/3, and then it's shifting a little bit to the right position. Finally, let's take a look on the data sheet of our sensor. Now the sensor that we will be using has a track from conductive plastic. This is the resistive track inside of the sensor. I have a picture that I will show you in a minute. And let's take a look on this here. For resistive position sensors, it is very important to maintain a limited current that is going through the sensor. In this case, you can see they recommend at maximum 1 milliampere. So if you are installing the sensor, you need to make sure that this is maintained, because otherwise you would heat the sensor and it would change its properties. Here is a picture of the resistive track made from conductive plastic. So here are my two fixed terminals, and here is the slider, the track for the slider, and here is the slider itself. So this is sliding along this, and it's changing the resistance that we actually measure. Finally, let's take a look on some example applications. On the left, you can see an injection machine for shoe production. So it's a plastic injection machine, and this is the resistive position sensor. This is the fixed part that is attached to the frame of the machine, and this is the slider that is measuring the position of this part of the injection machine. And the second example is an experiment to measure the friction coefficient, and one of the variables that was here measured was the position, and you can see here that this is the resistive position sensor. So now you will get the data, and you will be given the tasks by your lab teacher.